Okay. Good evening, students. So this is our sixth interactive session for soil mechanics. In previous week, we were discussing stresses in soils. Okay. So in previous week, we were discussing stresses in soils, and we had done some questions on the distribution of soil stress along the horizontal as well as the vertical. So in week 6, uh, you have studied the shear stress in soil, but it is it's only a very small part of this whole. This is a huge chapter. This is a huge portion of soil mechanics, a very important portion of soil mechanics. And what has been covered in week 6 is only a small part of it. So I don't want to spend today's lecture entirely on this. By the end of the lecture, we will do some questions on this and like we'll do some questions on stresses in soil, and then we will discuss about the shear stresses in soil, and then do a question maybe about Mohr circle. Okay, so let's. Is that fine, class? Okay. Um, okay. So let's move on. Let's first actually recapitulate what we studied in the previous uh, interactive session. So this is just a moment. The fifth interactive session. Okay. So in the fifth interactive session, we studied about, okay, stresses in saturated soils with and without seepage. Okay, and then we did some questions on this. We plotted this in Excel and saw how this comes out to be. Yes, and measured this. Okay, so let's see. We did not directly use Westergaard or uh, Bose yet. So point load of magnitude 100, 200, and 400 kilonewton. Let me check. Hello? Yes, yes. Can you hear me? Can you hear me? Uh, are you not able to hear me? Hello? Are you not able to hear me? Okay. Now you can hear me? Okay. I'm very sorry about that. Okay. It's okay. It's okay. So, you have gone through the material that has been uploaded up till now. Have you gone through the material that has been uploaded up till now? Yeah. Have you gone through it? I'm asking you. I'm asking you, have you gone through it? Uh, okay. So I'll just brief you. Uh, this is our sixth interactive session, and okay, you actually go through these materials that has been have been provided, and whatever I and there is one more TA associated with this course. Whatever we um, teach, we upload it on a YouTube channel that is dedicated for this purpose, and that link for that also you will get in the NPTEL forum, and you can check all the videos, all the interactive sessions that have been covered till now. Okay, how many members? I don't know that. Okay, yes, yes. Actually, unfortunately, not many people. Unfortunately, not many people join the interactive sessions. I but I would recommend that you join the interactive sessions, because that way you can first hand ask all the questions that are confusing you. You understand what I'm trying to say? Like, you can in real time ask whatever uh, your doubt is. So yeah. So we have a load, point load of magnitude 100 kilonewton at B, 200 kilonewton at C, and 400 kilonewton at D. Okay. Determine the increase in vertical stress at a depth of 6 meter below. So this is the plan basically. This is the top view of a field, let me say. So this is a plan, and you have 3 points here, here, and here, on which you have applied point loads of 100, 200, and 400. So it is in the side view, it will just seem like you'll have, actually let me draw it here. If you just try to see from a side view, you will see A point here, you will see B point here, and C point will be farther, but it will still be here, and D point will be here. So that will be the side view. But right now, in stresses, we deal with mostly polar coordinates. So we want to find this distance, this distance, this distance, and this distance. This will be R1, R2, R3, and then Z has been given as 6 meter, isn't it? So let's try to calculate. If you use the Boussinesq equation, let me, okay, let's actually draw a table so it is more legible to us. Okay, so we have load points B, C, and D, and then we have load in kilonewton, which is 100, 200, 400, and let's calculate this R distance of these points directly from A. R in meter will be, for B, this is only 6 meter. For C, it will be 6 square plus 6 square, but under root. So I can write square root of 36 plus 36. And for D, it will be, if I take this triangle, this is 3 meter and 6 meter. Square root of 3 square plus 6 square. 9 plus 36. Let's calculate that. This will be almost 8.5 meters, and this will be 6.7 meters. Let's write with some significant numbers. This was 4.8. And now we know the Z for all the cases, for all the points, it is 6 meters. Okay. So let me make this a little less shabby. Now we can calculate R by Z. This will be 1. This will be 1.41. This will be 1.118. So if you look at the Boussinesq equation, let me write it down here. It will be delta of increment of vertical stress is equal to 2 times Q Z cube over pi 1 plus R over Z square, and we have this square. So this was Z square at 4 2q by Z, I think. Let me verify again. Let me check the next equation. You are not able to hear me? Are you able to hear me? No. Are you able to hear me? Okay, just give me a. My screen is absent, but my voice is okay. Okay, let me share my okay. Let me don't worry about that. Entire screen share. Can you see my screen now? You can't see my screen, but I am share. Okay, so if yeah, if there is any problem, you just let me know. Okay, I did not know that my screen was not uh, visible. Okay, okay. I'm sorry about that. Excuse me. Let me recheck the Boussinesq equation. Doesn't matter. Your maths and your logic should be good. Your understanding of concepts should be good. It is just a medium of communication, language. Okay. But you do understand what I am saying. I'm checking the Boussinesq equation if we are writing the correct equation. I have to find the PDF for that. Just a moment. Okay. Till then, you can check this question that we were trying. Mm. I'm fine. I'm checking the Boussinesq equation. Okay, this is fine. Okay, this is the equation that I've written on the screen. Okay, that's the equation. I was just verifying it. Yes, that's it. 2q over pi z. Yeah, that's it. Okay, so let's calculate for. So I mentioned that we have a load of 100 kilonewton here. We have a load of 200 kilonewton here, and we have a load of 400 kilonewton here. And this whole is the plan. Like this is the top view. This is a field that you are looking at from the top. So if you look at it in the side view, you will find A here, you will find B and C here, but C will be farther, but in the same line. B and C, and D you will find here. Okay, so what Boussinesq equation tells us is if you have a point load or a line load, any kind of load, the loading is taking place here, and we want to calculate the effect of this loading here. What is the increase in vertical stress here? See, why we say increase in vertical stress is because as we go down in soil, due to the self weight itself, you will have a stress here. It will be the stress due to the uh, column of soil over this, just like water. When you talk about water, as you go deeper into the ocean, there is a lot of stress over this point because there is a column of water over this point, and the weight of this water will cause gravitational load over this point. Same goes with soil also. With the uh, force of gravity, along the force of gravity, there will be a stress in the downward direction if we take this point due to the self load of the soil. But say you are loading the soil here, it does not mean that only the soil particles below this will get loaded. There will be a distribution of this load along the soil, and this distribution takes place in this kind of a pattern, that most of the stress is taken by the particles directly below the point load, and then as we go away from this point load, the stress on the particles decreases. But nevertheless, there will be some effect on further particles. So this equation, it tells us about this equation of Boussinesq. It tells us about what is the, if we have a point load P or Q for example, if you have a load, then at a depth of Z, okay, at a depth of z and at a radial distance of r. As in, from the top view, we are not taking x and y, we are taking r in any direction, because this is a point. It can, it will influence in all the directions about it, isn't it? If it was a line load, we would be talking about perpendicular to the line load. But since it's a point load, we have all the directions to take. So we take r, which is the radial distance. And this tells us the increase in the vertical stress due to a point at a distance of r and a depth of z. So the question tells us that there are 3-point loads around a point A, and we want to calculate what will be at a depth of z is equal to 6 meters, what will be the increase in the vertical stress due to the presence of these points. Okay, so we calculated, we know P has been given. For B it's 100, then 200, then 400. R we could see, this is R we could see, for B R was 60. For C, R will be, this is 6 meter, 6 meter. This is a right angle triangle. This will be 6 square plus 6 square under root, isn't it? And then for D, if I take a perpendicular here, I need this radial distance, and this radial distance, isn't it? So I take this as a right angle triangle, and this will be under root of 3 square plus 6 square. And that is what we calculated. We calculated the r values, and we know the z values. We calculated the r by z value. Now we will calculate the sigma z for each point. Okay. Let me calculate. Over pi into 1 over 1 plus r over z is 1, and then r square. Mm, okay. Divide by 6. I forgot to divide by 6. Okay. 2 into 3. So 2 into 2 divided by z 5. Okay, so this comes out to be, you check this formula on the book. This comes out to be delta, sorry, d sigma z comes out to be 0.234 for this case, 0.173 for this case, and 0.72 for this case. Let me write this in this form because there is some error with the equation that I have written. Delta z will be equal to 2 cube z cube over pi times x1 plus x2 square plus z square whole square. Okay, and the total effect will be 1.127 kilonewton per meter square. So that is about the Boussinesq equation for point load. And if we have a line load, like here, let's talk about the line load. We need to determine the vertical stress increase delta sigma at point A with the following values. We have Q1 equal to 90 kilometer per meter. 90 kilometer per sorry, kilonewton per meter means per meter in this direction. 1 meter per meter. Like this will be 90, and then for the next 1 meter it will be 90, then for next 1 meter it will be 90. So 90 kilonewton per meter. Okay, so next Q2 we have, this is 90, this is 325. And we have x1 which is 4 meter, and x2 which is 2.5 meter. Okay, and then we have z which is 3 meter. So we want to calculate, like there is a line load here, something like let's say that there is a wall here and a wall here. If I watch it from the top, there is a wall here and it is producing a self weight of 90 kilonewton per meter. This is producing, this is maybe a concrete wall, so it's producing a higher load, 325 kilonewton per meter. And now I have a point which is, the distance between these two walls is 4 meter, and I have a point at a distance of 2.5 meter from the second wall. Okay, and at a depth of 3 meter from this point, I want to calculate what is the effect of load from these two walls. Okay, so this is what the question is saying. So we have is fine. So we have a equation for the line load also. That has been dealt with in the class. So I will be going on with that. Let me check the relation. Bahan, are you in the sorry, Bharat? So don't get confused. I know you might be getting confused. So the lectures right now, these are the what I am covering. These are interactive sessions, as in whatever you have studied in the week, in the lectures from Professor Bedia. So whatever has been covered through the week, I just go. I just um, go over these concepts using some numericals. So this is not like mm, because you said it's your first class and you might be thinking that I'm not explaining anything. But the explaining part has already been done in the lectures. My job is only as the TA to help you understand these numericals and help you understand the application of the things that you have studied in the class. So don't get worried that I'm not explaining anything to you, okay? Or if you want me to, I will explain also because it's your first class. Do you understand? Okay. So because this is your first class, you might be thinking that nothing is getting explained, but the explaining part is the uploaded videos that you will get that are present in the YouTube channel of this course by Professor. The NPTEL, have you enrolled for this course? You have enrolled for this course, haven't you? Yeah. So on your account of NPTEL, you will get these notifications of the um, course that week one lectures have been released, week two lectures have been released, and that is where explaining of the principles will be done, and in the interactive sessions we will just go over questions. Okay, okay. So, see, this is a simple concept again. You have a line load formula, which is delta sigma z equals 2 times q z cube over pi x1 plus x2 square plus z2 square. Okay, x. Let me write x here for being general. So here we will have the effect due to load 1, effect due to load 2. So for load 1, X is, for load 1, Q is 90, X is 4 plus 2.5, 6.5. Okay, and Z is 3 meter. For load 2, Q is 325, X is 2.5, and Z is 3 meter. And we calculate delta sigma Z as 2 into 90 into Z 3 cube over pi 4 plus, this is, one second, 2.5, this is 6.5, 6.5 square plus 3 square plus 2 into 325 into 3 square, sorry, 3 cube over pi 2.5 square plus 3 square, the whole square here. So let's calculate this. So delta sigma Z comes out to be 24.6 kilonewton per meter square. Okay. Okay. Let's take a short break, Bharat. What? Okay. So these were some questions that we saw for stresses in soils, and now let's do some questions on Mohr circle. I know it's a very introductory kind of thing that you studied in this week, but let's try to solve this. Okay, and so we have been given. This is something that you might have studied in your solid mechanics. You study these free body diagrams. So we take a small section of soil, say the soil is present at a particular depth, and we take this section of soil, like we dig this out, and we try to analyze that what are the forces and the stresses. Forces will be the external, basically what is the stress force from above due to self weight, what is the force from here due to lateral pressure of soil, and on in response to that force what are the stresses in the soil. So what stresses means is, like, if you take a fabric, you try to pull it, so it will have threads in this way and threads in this way. When you try to pull it diagonally, you see you will get some this type of shape for your fabric, isn't it? So what you're doing is you are applying shear stress to your fabric because the strength of the fabric is in this direction, isn't it? Along these, if you pull, it will not stretch that much. Along these, if you pull, it will not stretch that much. But along this, so this will be a normal force on your fabric along the horizontal threads. Along the vertical threads, there will also be a normal force. But if you try to pull in this direction, there will be this shearing type of force. So whatever type of force that you use on a body, what will happen is, on in response to that, there will be some stresses that will be generated inside the body. Stresses will be generated inside the body. So what happens is that the body that you have, this is a three-dimensional body. You can have infinite number of planes that can pass through this body, isn't it? So on any one of these plane, you take and you try to calculate what is the normal stress on this particular segment. I took this segment. I'm trying to see that due to the force, external force that I have created over this, what is this for this stress, normal, and the shear stress along this. Okay, which type, like how much stress is there that is trying to compress it, or that's trying to like pull it, or that is trying to share it. Over these infinite planes we cannot do na. So we have the concept of principal stress for that. We take that particular orientation of plane out of these infinite, we take these particular orientation in which our shear stresses are zero. Okay, so that is the concept behind our principal stresses. But now, how do we calculate these principal stresses? Right now, this is not the principal plane. The stresses on the principal plane will be principal stresses. Right here, I can see the normal stresses also and shear stresses also, which means that this is not the principal plane. Why? Because on principal plane, you will only have normal stresses. Or this, you will not have shear stresses. This will not be there. This is when you draw a free body diagram on this plane, if you are pulling in this direction, it cannot be only in one direction, because this means that the body is getting dragged in this direction, but which is not true. If you see a soil, there is load on this soil, but it is stationary. So there is also a downward pull, which is keeping this stationary. So this is one force. Let us call this Fy, sigma y, and then there will be maybe a compressive force in this direction. It is also in pair, because only one direction will mean that the soil is running in this direction, which is not true, because this is in equilibrium here, this is static here. Let's call this sigma x, and the shear, let's call this tau. So if you are doing this, if you're only when you provide this opposite force here, can you call this shear? Because if I only provide it in one direction, it means that I'm trying to rotate this body. It will rotate here. But because I am applying a force here, or creating a stress such that there is a stress here, so this is, let's call this is on the, this is tau x and tau y. Okay. From simply calculating this, just a moment. Okay. So if we calculate the resultants of these, and we draw this free body diagram, and then we equate in the x this direction forces in the horizontal direction, forces in the vertical direction. We get these equations. So we know we have equation for normal force and the tangential force. So the equation for normal force is sigma y plus sigma x over 2 plus sigma y minus sigma x over 2 cos of 2 theta. Theta is this, okay, plus tau xy sine of 2 theta, okay. And further we will have tau equals sigma y minus sigma x by 2 sine 2 theta minus tau xy cos 2 theta. Remember, this is x and y, which means this is on any ordinary plane. This is not on principal plane. If this was on principal plane, then this value would have been, this and this would have been 0. In fact, that is how we calculate value of maximum and minimum principal stresses, when we give the value of shear stresses on these planes as 0. Okay. Now for maximum principal stresses, we have basically, okay, that is in the next lecture, how to calculate the principal stresses. For now, let's try to calculate. We have been given that there is this soil element. The sigma x is 120 kilonewton per meter square, and this is sigma y, okay. Sigma y is 300 and tau is, I have written it, this is 40, okay. You have sigma y, which is 300 kilonewton per meter square, and then you have the tau, which is 40 kilonewton per meter square. Then tau here, which is equal in all places. Okay, and this angle is 20. We have to calculate the magnitudes of the principal stresses. So first of all, magnitudes of principal stresses. We call these principal stresses as sigma 1. Actually, there are three principal stresses because we have three coordinates. We call maximum principal stress as sigma 1. We call minimum principal stress as sigma 3, which can be in this case also. But sigma 1 is always greater than sigma 3. Okay, so we have the formula for sigma 1 is sigma x plus sigma y over 2 plus minus sigma y minus sigma x over 2 plus tau xy square. And sigma 3, like sigma 1 is positive and sigma 3 is negative. So sigma 1 will be x is 120 plus 300 over 2 plus square root of 1. I mean the same thing, there is a square here, 120 minus 300 over 2 square plus 40 square, and sigma 3 will be 120 plus 300 over 2 minus square root of 120 minus 300 over 2 whole square plus 40 square. Okay, it's actually minus 40 square, but it's the same thing because there is a square there. Let's duplicate the slide. So let's calculate. So the sigma 1 will come out to be 308.5 kilonewton per meter square, and sigma 3 will come out to be 111.5 kilonewton per meter square. Okay, so the next question is normal and shear stresses on plane AB. Okay, normal and shear stresses. So this was just the horizontal and the vertical stresses. Now let's calculate the sigma n and the tau n is equivalent to, as I mentioned here, here sigma y minus sigma y plus sigma x over 2 plus sigma y minus sigma x over 2 cos 2 theta plus tau xy sin 2 theta. Okay, let me write it again here. Sigma n will be sigma x plus sigma y over 2 plus sigma y minus sigma x over 2 cos 2 theta plus tau times sin 2 theta. This will be 300 plus 120 over 2 plus 300 minus 120 over 2. Yes, sigma is this n. Sigma n is the normal stress. Like, normal and shear stresses on plane AB. See, this is the whole element. Now we are talking about only A and B. Okay, we are talking about AB plane. Okay, when we talk about this plane, how we represent stresses on a plane, here you see there is one normal stress and there is one shear stress. That is what we do. We take a normal stress and we take a shear stress. Okay, this is the shear stress. So we are calculating the tau n and sigma n on this plane. Do you understand that? Do you know why we are calculating it over a plane? As I mentioned before this, that when you have a body which is three-dimensional, okay, we have a three-dimensional body. Now you are applying some external forces to it, many external forces to it. You want to assess what is the stress in the body due to these forces. What we usually do is we take a cross section, isn't it? We take a cross section of this body at any random point. But our calculations should be such, our assumptions and our deductions should be such that our formulae should not depend on the location of this uh, cross section point. Wherever I cut this cross section, I should get the same results. But when I talk in this form, form of sigma x and sigma y, I am making my result dependent on sigma x and sigma y, which are very which are particular to a particular plane only. They are not general. For a generalized result, we calculate sigma 1 and sigma 3. These are major and minor principal stresses. These are stresses on that plane which does not have any shear stress. Like there is a rotation of plane going on inside the body. As you change these planes, your sigma x, sigma y, tau, etc. will change as you change the theta. You see, tau n is changing and this is changing for the same body, for the same element. If I'm not taking AB plane, let me take some other plane. Let me take this plane. It will have a different theta. will be theta 2. And then here we will be having theta 2 and theta 2, isn't it? Then our sigma n and sigma tau will be different. But in case of sigma 1 and sigma 3, if you see sigma 1 and sigma 3, they were free of any cos or sine theta, so which means that they will not depend on the orientation of the plane. Do you understand? Their value, I mean to say, of the failure plane. Okay, so tau n is, first let's calculate the sigma n. 300 minus 120 over 2 cos of 2 into 20 plus minus 40 sine of 2 into 20. This comes out to be 253.23 kilonewton per meter square. For tau n, we have sigma y minus sigma x over 2 sine 2 theta minus tau times cos 2 theta. This will be 300 minus 120 over 2 sine of 2 into 20 minus tan 40 cos of 2 into 20. This comes out to be 88.4 kilonewton per meter square. This is tau n, and this is sigma n. We have one more question that we can discuss, but because we have to plot it, it will not be possible to completely show this, but I will give you an idea. So for a stressed soil element, how can we calculate all this that we have done in the previous class, previous question, but graphically using Mohr's circle. So in Mohr's circle, what we do is we take here, this is 50 and 150, but tau in this direction is positive and tau like anti-clockwise is positive, clockwise is negative. So if you see, this is clockwise, this is negative, this is minus 50. We take an axis, we plot normal stress here, we plot shear stress here. Okay, so the normal stress here is 50. Normal is 150 and shear is minus 50. So we will plot somewhere here 150 comma minus 50. This will be the first point. Okay, based on stresses in this direction, in the horizontal direction. Then we will plot this point, which is 50 comma 50, somewhere here. This will be 50, comma 50, because our shear stress as well as the normal stress is 50. And now what we do is we connect these two. Wherever they meet here, this is the center of Mohr circle, and we draw a circle with this as diameter. Okay, sorry for this ridiculous drawing. We draw, this will be the diameter, and we draw this circle. Okay, and then from any known point, for example this, see, this is the plane on which we want the stresses, isn't it? So what we will do is first we will take a vertical line through this point that will indicate, we will take a vertical line, and then we will take angle 10 line. Okay, this is called the pole of the Mohr circle. These 2 points from these two stress states we calculated, then we joined them and we created a circle around them. And let me try to do this over. I was actually before this trying to do this in AutoCAD. I'm not sure, I'm not very well versed with it. I was, but right now I don't remember much about it. So let us try. Okay, we have a line 150 minus 50, isn't it? Let's draw this line. Oh, okay. So let's draw a line. 150 minus 50, the first point. And then we have another point at 50 and 50. Okay, so this is the line. Then we take a circle. Uh, this will be the first end point of the diameter. My mouse is lagging, I'm sorry. This will be the second endpoint of the circle's diameter. So this is a Mohr circle. Okay, this will be our Mohr circle. And now to plot the pole, what we will do is we take a line and we -90 degree up to here. Oh no, it happened. Yeah, I'm having some issue with lagging, but let's try it one more time. Okay, here it will start. Up to here. So this will be the pole. This point here. Uh, how do I insert a point and okay, having some issue. This will be the pole. Okay, and from the pole, what we want to do is from the pole, we want to consider this as this side of the soil element. So we want to take a line 10 degrees to the east. Okay, so let's try to do that. So this is 10 degrees. Oh no. Okay, I had to take not 10, but this should be 10, this should be 280 degrees. This should have been 280 degrees because this is the third quadrant. Okay, yes. So you see right here, I'm having some trouble with my mouse. I'm sorry about that. But right here, if you check, let's zoom. It's not keen on zooming. Yeah, so let's try to just, this is about 163 comma minus 29. So the stresses on the plane that has been mentioned here, the stresses on this plane will be about 163 and 30. The shear stress will be 30 and normal stress will be about 163. If you calculate it according to your formula, you can cross check it. Okay. I think that is all for today, and best of luck, and let us meet next week for the next interactive session.